Okay, welcome to Chapter 6 in our Zane State Physics 2010 class, where we are going to start talking about work and energy. So, work is a word that is obviously commonly used. Many people think they know what work means, but in the physics context, it means something very specific. So basically, work is done when you apply a force to an object and move it some distance. So in the example here, we have this lady pulling on a rope attached to this box, and it's going to slide across the floor. When she moves that box across the floor, she is doing work. Now, the little wrinkle here is that she is not pulling in the same direction as the box is moving. And work is done in the direction of the motion. So what we have to do is, since she is pulling at this angle, if we wanted to know how much work she's doing, we would need to find the x component of that vector, of that force vector that she's applying. And we find the horizontal component by taking her force times cosine of theta, of the angle that she's making. So basically, if we take the horizontal component of her force that she's applying and multiply it by the distance that the box is moving, that is what gives us work. And so that's where this formula comes from, FD cosine of theta. Now, if she was pulling perfectly horizontally, parallel to the motion of the box, this equation would be simplified and it would just be work equals force times distance. Work equals FD. But because she's not pulling in exactly the same direction, we need to find the horizontal component, and that's where the cosine of theta comes in. In the metric system, the units of work are called joules, named after James Prescott Joule. And the thing to keep in mind when we are determining how much work is being done on an object is that, just like in the previous slide here, like the woman pulling the box, the work, or the force being applied to the object has to be parallel to the direction of motion in order to create work. In this example, on this slide, the gentleman here holding the grocery bag, even if he moves in a forward direction, he's moving the bag. Okay, but let's take a look at the other forces that he's applying. There's the weight of the bag itself acting down due to gravity, and he's holding it up. And the motion is horizontal. So theta, the angle here, is 90 degrees. If we take cosine of 90 degrees, you'll find that that is 0. So he is doing 0 work on this bag of groceries. And the reason for that is because the force he's applying is perpendicular to the motion. So it can be a little tricky because intuitively it thinks, well, of course he's doing work. But strictly speaking, in a physics sense, he is not, because of the orientation of the force he is applying and the direction that the bag is moving. So there is no horizontal component to his force, therefore the work being done is 0. Now back to a joule. A joule is an example of a derived unit, and it is equal to, if we think of what work is a force times a distance, FD, and our unit of force is the Newton, and our unit of distance is the meter. So 1 joule is equal to 1 Newton meter. Let's look at an example here where we have a crate on the ground, horizontal ground, and we're going to apply a pulling force. at an angle of 37 degrees. And then we're going to move it 40 meters across the floor. The force that we're going to apply is 100 newtons. And the friction force is given to us. We're not going to need to calculate the friction force. We could if we knew the coefficient of friction and the mass of the crate, but instead they've just given us the force here of friction is 50 newtons. We want to know how much work is done on the crate, and then what is the net work done on the crate. So this will illustrate the difference between work and net work. So this example is almost exactly like the slide that showed the woman pulling on the rope to move a box. And on that slide we said that work is equal to FD cosine of theta. So our force being applied is 100 newtons. The distance traveled is 40 meters, and the angle between the line of action of the force and the motion is 37 degrees. So if we take 100 times 40 times cosine of 37, that gives us, it actually gives us 3195. But if we round that to significant figures, now again, here's something that the author does that kind of drives me crazy. Things like this, 40 meters. Is that one or two significant figures? Technically speaking, it's only one, but the author intends for it to be two. That's exactly 40 meters. So, and that's 37, that's obviously two. And the 100, is that technically just one, or is it three, or I don't know. But the author uses two significant figures here, so it's 3200 joules. So that is the work that we are going to do on the crate in order to make it move. But while we are doing work to move the crate, friction is also doing work trying to stop us, working against us. And so that work is that is done by the friction is also W equals FD cosine of theta, except in this case theta is 0 because friction is moving in the same direction. Actually, I guess we could think of our direction here as being 180 degrees because it's going in the opposite direction as the motion. So our force due to friction is 50 newtons. The distance is 40 meters. And the angle is cosine of 180. Cosine of 180 is negative 1 times 40 times 50. And that gives us negative 2,000 joules. So while we are doing work to the right, friction is doing work to the left. It is doing something called negative work, which may seem like sort of a strange idea, but it's basically just work being done in the opposite direction. So that leads us then to what the question asked for. What is the net work? The net work is our positive 3,200 joules minus the 2,000 joules of work being done by friction, and we end up with a positive net value of 1,200 joules. So if you've ever had a job and looked at your pay stub, you've got your gross pay and your net pay. The net pay is what you're left with after taxes and things like that are taken out. So that's similar definitions to what we're talking about here. The net work is the work that we're left over with after we take out what has been done by friction. So this is the net work that is being done. So friction is one source of negative work. Gravity is also another thing. So these are kind of things that work against us. I've chosen this image here because they're kind of like these cartoon villains that are always trying to foil our plans. They're always trying to undo what we are trying to do. And these are just things that need to be overcome in order for a mechanical system to work. Let's look at another example here where we have a hiker with a backpack that's going to go up an incline, and we want to know how much work the hiker does on his 15-kilogram backpack. The force he exerts on it is straight up. So we're going to imagine that in order to keep the backpack suspended, he is applying a force on the shoulder straps probably, and we're going to assume that force that he's applying is straight up. So what we have to remember is that the work being done on the backpack has to be parallel to the motion. So we end up here, if the work is straight up but he's moving at an angle, those two things are not parallel to each other. And that angle turns out to be theta, because we have two parallel lines intersected by a third line, and the alternate interior angles are congruent. So this is given to us as theta. If that's theta, then so is that. So that's the difference between the line of action of the force and the line of action of the motion. So the force that is required to hold the backpack up is going to be equal and in opposite direction to its weight, mg. So this is equal to mg in order to hold it up. And if we look at these forces, we've got the force holding it up and the weight pulling it down, and then this inclined slope. And I have rotated this image to make the distance horizontal so that it is similar to our example of sliding a crate along the floor. So the work being done by his force is that force is going to have a vertical and horizontal component, and it's only the part, the horizontal component that is parallel to this distance that is going to do work. So work equals FD cosine of theta, and the force that he's applying, FH, is equal to mg times d times cosine of theta. Now, what is the distance along this inclined slope that he is traveling? If we look at our right triangle trigonometry, we are given in the problem statement that the height is 10 meters. So what is the hypotenuse length here then? So if we know this angle, this is the hypotenuse and this is adjacent. So we have adjacent and hypotenuse. So is it so, ka, or toa? It is ka, or cosine. So what we're saying here is that cosine of theta equals the adjacent side of 10 over the hypotenuse, which we're going to call d. So therefore d is equal to 10 divided by cosine of theta. So we can take this and plug it in for d here, and so this becomes mg times 10 over cosine of theta times cosine of theta. And I'm going to have to resume this in the next video.